Recording in progress.
Yeah, comes on everyone. Yeah, so last class we were doing this water equivalent, heat capacity, specific heat, and all this stuff. Perfect. Next thing. Latent heat of fusion. The symbol is LF. This is amount of heat required to melt 1 unit of solid. Into liquid. So basically, this is when the solid converts into liquid, right? We can't use ms delta T because there's no change in temperature. We use something else. So here the heat is given by Q is equal to M into LF. Example, latent heat of fusion of ice, you should remember this, is 80 calorie per gram. That means if you want to melt 1 gram of ice, you need to give 80 calories of heat. So this is the formula which we use whenever there is a phase change. So when solid converts into liquid and liquid converts to gas and stuff, this is the formulas which you will use instead of that ms delta T thing there. Now, when someone saw this thing, this is what happens, this Instagram and all, people see this kind of stuff, they know half science. So someone came with a brilliant idea. Why don't we do something called an ice diet? So your breakfast will be ice cubes, lunch will be ice cubes, dinner will be ice cubes with a pinch of salt and a lime for taste. It is called ice diet. And their idea is this. So first of all, since you're eating ice, there are no calories on top of it. Where do you get this 80 calories heat from? From your own internal body temperature, isn't it? So your body ka calories are burning out. Now, idea looks fine. The problem now, imagine you eat one dairy milk silk. Getting it? One full dairy milk silk has how many calories? Roughly around 560, 570, that big one. So roughly around, that is 600 kilocalories. Getting it? So when you say you're eating something, you're actually burning kilocalories, not calories. Right? So now in order to burn this much, yeah. So in order to burn this much, how much ice should you eat? So this is 600 kilocalories. That is 600 into 10 power 3 by 80. 0 goes off. This is 2, this is 15. That's around 7.5 into 10 power 3 grams. So 7.5 kgs of ice. So if you want to burn that 500 calories to 600 calories, you need to eat around 7.5 kgs of ice. A very bad idea. Never try this, because first thing what will happen, your core temperature will drop. Right, and when the core temperature drops, all your blood and everything, basically your entire system is trying to keep you warm, so your immunity system drops. That is the reason during winters people get a lot of cold, flu, and infections, isn't it? So your body, instead of doing all necessary things, it is fighting to maintain the temperature, so your immunity goes down and you'll fall sick. Worst case, you'll get a hypothermia, right? And yeah, game over. So not a good diet. So that is there. Niharika, there is only one profile of yours, right? The other one left, I
Oh,
guess.
okay. Thank
So
you.
that is one. So keep that in mind. So latent heat of fusion of ice is 80 calorie per gram. The next one is latent heat of vaporization. We'll call this thing LV. This is the amount of heat required to vaporize 1 unit of liquid into gas. So here the formula will be Q is equal to M into LV. Example, if you take latent heat of vaporization of water, that means when you boil water and you want to vaporize this comes out to be 540 calories per gram. Quite a large value actually. 540 calories is pretty large value. One of the reason why Earth may still the water exists. Imagine instead of 540, it is 54. You know the meaning of it? Every day, 10 times more water will vaporize into the atmosphere. So your floods and rains will be 10 times more stronger. They will be swept away actually. And ever think about this thing, when there is a fire or something, these people, put a lot of water. Why do you think they do that? What is the main purpose there? I used to think, you put so much water, oxygen supply gets cut off and fire stops. Not completely wrong, but that's not the main reason there. The thing is, when you put a lot of water, wood has an ignition temperature of 800 degrees. That means until you raise the temperature to 800 degrees, wood won't catch fire. So let's say if a building is on fire and you start dumping a lot of water, what will happen? The water will start absorbing all this, this heat. The temperature of the system drops. So the new wood will not catch fire. Getting it? And whatever wood is already on fire, if you can actually dump water on it, you can cut off oxygen supply and make it extinguish. So it does two purposes. But there is a problem. If the surface gets really heated, water actually becomes a bad idea. This thing, you can try this at home actually. This milka pan is there. You take this milka pan or actually your dosa ka pan, right? Just keep it on the stove for 1 minute. Don't put anything, just keep it on the stove for 1 minute, gets heated up. Now, if you put water inside, you get this kind of sound, isn't it? Basically, it vaporizes. But if you keep this on the pan for 2 to 3 minutes without anything inside, first thing your mom is going to beat you right and left. But let's say that doesn't happen. You will observe this whole thing actually becomes reddish. Ever tried? The whole thing becomes reddish. Means the temperature has gone really high. Now, if you put water in this, you will notice something interesting. The water will not vaporize. Instead, it forms droplets and it starts floating inside. Ever seen that? When the dosa ka pan is very hot, if you put water, it won't get that sound. Instead, the water forms a bubble and floats. This is called Lindenfrost effect. So what is actually happening is the surface is so heated, let's say 1,000 degrees or something, and when the water is falling, the moment the water hits, the bottom part gets vaporized. So this entire thing will have a water vapor. The remaining water is floating on top of the water vapor. Did you ever play that air hockey game in the time zone? वो game है ना, this thing you will see in the malls, that game, there are a lot of holes here and there is a striker is floating on a stream of air. If you have played that game in the time zone, kind of behaves like that. So this water now is not touching the metal, it is floating on this water vapor. You can see this happening with liquid nitrogen also. If you take a cup of liquid nitrogen, drop it on the floor, it will just form bubbles and will run away from everywhere. Did you ever get a chance to see liquid nitrogen? Rare, I guess. Yeah. Even I saw it in the IIT ka lab mein, na, we had a superconductivity experiment. So they gave us a glass of liquid nitrogen. We used half for experiment and remaining half for doing nonsense. So yeah. But I heard in Matunga there is some restaurant which actually, gives you ice creams made of liquid nitrogen. So the idea was this: when you make ice cream, right? Normally, what they do, they use milk. But the problem with the milk is it does contain amount of water. So when it freezes inside, right, you get water crystals. So taste actually gets slightly diluted. So these people have an idea. Instead of using milk, they use liquid nitrogen to mix the whole mixture. And at normal temperature, what will happen? Liquid nitrogen will become gas. So now you have, instead of water crystals, you have cavities. Your ice cream looks more fluffy, like cotton candy. So it gives you a taste. I never ate it. I just heard about it. I'm not sure whether it is still open or not. So they use liquid nitrogen. So this is called Lindenfrost effect. You can definitely try this on a hot dosa pan. So now when it gets really heated to 1,000 degrees, right, and if you try to put water, the water literally floats above that water vapor and the system doesn't cool down. One other thing that happened during a Chernobyl blast. These people, right, during the nuclear reactor, what is on a maintenance, they are doing some testing. They switched off the power supply to the generators, the water generators. So water pumping station stopped. All the water got vaporized. These people didn't realize the core temperature started rising. A nuclear reactor, right? Even if you are not operating, it still generates heat. So there should be water at 24/7. There should be water. These people didn't switch on the water pumps. Water completely got evaporated. Temperature started rising. It reached some around 1,000 degrees or something. Then they realized, shit, there is no water. Then they started pumping water. But like I said, Lindenfrost effect, the water was not hitting the metal or whatever. It is not cooling down. Eventually, the temperature went more than 1,500, 2,000. The core got exposed and there was a whole mess up. One of the reasons. So there are multiple reasons of failure, but this is one of them. So there anyway, so water 540, right, is a pretty large value. It actually removes a lot of heat. So one day I still remember 10 years back, I guess. You know that immersion rod aata hai? The heater ka thing, immersion rod, if you ever seen that. So that immersion rod, right? Normally you have a bucket, na? You just keep that immersion rod here and you keep it there for 25 minutes, half an hour, water gets heated up. So one day I kept the immersion rod. I went down, the society to get something. I went to the shop and while coming back, na, my friend came and said, Arey Arun, we will go to movie. Kya? I said, theek hai. Then we got an order and went to movie. I completely forgot I kept the immersion rod. Went to the movie भी खत्म हो गया. While coming back, na, something was hitting me. यार कुछ तो गड़बड़ है, कुछ तो गड़बड़ है. I'm not able to figure out what it is. Just before reaching home, na, then it hit me. I said, shit, I kept the immersion rod. It has been 4 hours. I was totally scared, like, yeah, kya hoga? Meaning, my first thing was maybe the bucket has completely melted. The house is on fire. I was imagining all stuff. Right? There'd be a fire engine in front of the house. Then we came to the house. I started running, went to the room and saw. Interestingly, what I found was something else. Half of the bucket water got vaporized, remaining still half bucket water is there. Because see, that's a big bucket. Okay, if you see a big bucket now, it has a capacity of around 25 kgs of water. Right? And this immersion rod was 2 kilowatts, meaning this was producing around 2000 joules per second. And if you divide by 4.2 calories, let's make it roughly 500 calories per second, right? And roughly that is like 1 gram per second. So you're only melting 1 gram every second. So into 4 hours, that is 3,600. So you're melting 3.6 kgs every second. So every hour into 4, that's around roughly 12 to 13 kgs of water got vaporized. Bucket was safe. House was safe. There was no fire engine. So, but water was superheated. Then I realized, shit, this LV na 540 I know, but I really didn't know how big it was that day. I realized it. 4 hours and I could only vaporize half the bucket of water. Anyway, so that is one thing. Next thing. So boil the water is easy, huh? Vaporizing water is very difficult. If I throw 100 degrees water on you and if I throw 100 degrees steam on you, right, which is more dangerous? Now you know. Steam is more dangerous. The steam, you can get killed actually. You'll get third-degree burns. 100-degree water is nothing. It's a joke. It will fall. You will get just burn and then it goes off. During this 1800s, during the steam engines and everything, the biggest accident was this only, steam deaths. During an accidental operation, right, the steam used to get leaked, and worst, that steam used to be at 200 degrees. That's a superheated steam. So, yeah, steam is dangerous. Don't underestimate it. You want to underestimate it, you can try this pressure cooker. When it gives out steam, put your hand and see. Takes 2 seconds to realize. Now, if you try to see what happens here, the whole process, the solid converts to liquid becomes gas. So generally, this is the process. There are exceptions. Carbon dioxide doesn't go through the liquid state. We call it sublimation. Right? This is called a phase change. And there are actually two other states of matter. One becomes a plasma, where literally you have removed all the electrons from the nucleus. It's a soup of. It's charged particles, and the other one is a Bose-Einstein condensate matter. Occurs at very low temperature. Liquid helium, these things have very weird properties. Liquid helium, right, starts climbing the walls. So they do behave pretty weird stuff. We'll not get into that. But there are 5 states of matter so far. So conversion is called phase change. Now, if you take a solid and let's say if you're heating, now listen to this carefully. So whenever you're heating something, right, this is the process it follows through generally. So let's say we have a solid. Now the molecules are compact. They're tightly packed. And let's say you're heating at a constant rate. So maybe every second you're giving some 10 calories per second. So if you're heating at a constant rate, first thing what will happen, all the energy is absorbed by the solid and the molecules will vibrate with more larger vibrations. Temperature rises. It still remains solid, but temperature increases because the kinetic energy increases, whereas the potential energy remains same. Now, if you continue to give more heat, now what will happen? That energy, right, is used to break the bonds. So the solid-solid bonds will break. So still there is some solid, but remaining is becoming water. So now you get a solid and a liquid mixture. So this is what you'll notice. If you take solid ice, and put it in a ice and put it in a glass, after some time you'll see some water, some ice ka mixture. Now in this process, temperature is constant. So all the energy that you're supplying is used to break the bonds between the molecules instead of using to increase the kinetic energy. Kinetic energy becomes constant. Potential energy rises. So the heat is used to break the bonds. So when you're breaking the bonds, potential energy changes. Basically, potential energy is the interactional energy. So they're interacting by that bonds. And then what will happen? It will come completely into a liquid. So the phase change is completed. If you continue to give heat, the liquid temperature will rise. So it still remains liquid. Temperature increases, kinetic energy increases, potential energy remains constant. So this potential energy changes, only whenever there is a phase change. And then if you continue to give more heat, the process is going on, Rehan. Suddenly you won't give all the heat. And then what will happen? You will realize we have liquid now and we also start getting vapor now. Means again the bonds are breaking. So again temperature becomes constant. So whenever there is a phase change, temperature doesn't change. So all the energy you're supplying is going for potential energy instead of kinetic. And temperature changes only when there's a random kinetic energy changes. And then it becomes completely vapor and then the temperature rises. The story goes on. Is the process clear, everyone? So you cannot directly jump from solid to vapor. You have to go through all these states. So if heat is given to the body, should the temperature change? True or false? Not necessary, right? May or may not change because there can be a phase change. So general notation, we think like here heat is given, the temperature change on a chain. Not necessary. There could be a phase change. Temperature may or may not change. Clear, everyone? Now, if I try to put this on a graph, turn in the page, all clear with this page. So if I try to plot this on a graph, temperature versus time. This is what you'll notice. So initially you have solid, temperature rises, becomes constant, temperature rises, becomes constant, temperature rises. So O to A, this is only solid, temperature is increasing. So A to B, did you see the line is horizontal, meaning temperature is not changing. So this is a solid liquid mixture. Basically, there's a phase change. Then it becomes completely liquid. So again, temperature rises. Then you have a liquid gas ka mixture. Again, phase change. Then it becomes gas. So whenever there is a mixture, carbon is exception. It doesn't have a liquid state. So there are few exceptions there. The bonds are so weak it directly goes into the gas state. You need to talk to your chemistry, sir. But that is the thing there. There are few exceptions. You must have studied, right? It's called sublimation. Yeah. So now here, if you assume the temperature, heat is given at a constant rate. This graph is important, right? They do ask questions. Then the heat supplied will be, let's say you're supplying Q joules per second into time. So this guy will be dq or ms dt. This will be q into dt. So we'll get dt by dt, that is the rate of change of temperature, is q by ms. This is nothing but the slope of the curve. You can clearly see slope is proportional to 1 by ms. That means, look at this graph here. So if you look at the OA, if you look at the line slope of OA, this is proportional to 1 by mass into specific heat of the solid. Ask yourself this thing. If you have higher the specific heat, means what? More difficult to change the temperature. Meaning it takes more time for the temperature to rise. That means slope should be small, no? Think of like this. If you have two liquids in this given amount of, let's say 10 seconds, you are giving same amount of heat. So whoever has more specific heat capacity should have less temperature compared to the one who has less specific heat capacity, isn't it? So if you look at the specific heat capacity of the green one, let's call it S1 and S2. S2 must be greater than S1. The slope is inversely proportional to the specific heat capacity. So higher the specific heat capacity, more difficult to change the temperature. So the y coordinate will be smaller compared to the x coordinate here. Similarly, if you look at the slope of BC, this will be proportional to 1 by, this is for a liquid, m into specific heat of the liquid. So the different line ka slopes will give you something else, different stuff. The slope of DE will give you the specific heat of the gas. Other than this, what about the AB ka length? So length AB is proportional to latent heat of fusion. Again, ask yourself, what is the meaning of this? Suppose instead of this line, if the line is this big, means what? It took more time for the solid to melt, isn't it? If you're taking more time to melt, means you require more heat to melt. Does that make sense? Imagine a substance took 1 minute to melt, another substance took 5 minutes to melt. Doesn't that mean the 5 minutes wala is 5 times more difficult to melt? Means it requires more heat per gram. So your latent heat is more. So the horizontal lines will give you the latent heat. The lines at an angle will give you the specific heats. The length CD is proportional to latent heat of vaporization. There, so quite a useful graph. It literally gives you everything: specific heats, latent heats of all the states. Have a look at this. More time implies more heat is required to melt. That means there's a more latent heat. Clear? Let's see a question based on this, how they'll frame a question. This is temperature versus time graph. Let's say this is liquid 1. So A, B, C, D. This is substance 1. This is substance 2. So compare for the solid, compare the specific heat S1, specific heat S2, then compare latent heat of fusion L1, L2, then compare for the liquid S1, S2, then compare for the latent heat of vaporization L1, L2, then compare for the gas the specific heats. There. The specific heat of the solid and solids ka comparison, specific heat of liquids ka comparison. So it need not be same for all. Maybe one substance ka liquid might be more than solid. Physical properties can vary a lot. So looking at this graph, you tell me which liquid in both of them, the liquid state, which is more difficult to vaporize or melt. There are 5 questions. Get them. If you look at the slope of OA, the green one will slope is more. Slope of OA for substance 1 is greater than slope of OA of substance 2. Slope is more, means it has less specific heat capacity. So the green one is more difficult to increase the temperature. Between AB, who has more length, AB has more length, so L2 is greater than L1. Between B to C, who has more slope, the green one. So this guy S1 will dominate. CD is smaller, L1 will dominate. This will dominate. Clear? So for specific heat, slope is proportional to 1 by specific heat. Latent heat is proportional to the horizontal length of the line. Clear, everyone? Easy, but you should know what does that slope mean and everything. So be careful with that. Any doubts on this? Clear, na, Arush? Arya, Sharman, clear? Next one. We have 100 grams of ice at minus 50 degrees. How much heat is required for a gas? Who has more slope? I wrote wrong. S1 greater than S2. D ka slope is more. You're right. So 100 grams of is minus 50 degrees. So how much heat is required to vaporize this to 200 Celsius ka steam. So if I want to make this into 200, so 200 degrees ka steam, how much heat should I give? So the ice is at minus 50 degrees. I wanted to get the steam at 200 Celsius. Specific heat of water is 1 calorie per gram per Celsius. Specific heat of ice and specific heat of steam. I did right before. I'll just put it again. This is half calorie per gram per Celsius. Latent heat of fusion of ice is 80 calorie per gram. Latent heat of vaporization of water, 540 calorie per gram. There, you need the data. Get it, I'll give you a minute. It's just brute force substitution, there's nothing there. But remember, directly you can't go from ice to steam. It goes through that states. Let's see. 79,500. Yep. 20 seconds more. Let's see. So understand, directly you can't become water. First you have to become 0 degree ice. So this will become 0 degree ice. Then you will become 0 degree water. Then you will become 100 degree water. Then you become 100 degree steam. Then you become 200 degree steam. So there, this is how you go through. You have to go step by step. So here, now see, whenever you're just changing temperature, use Q is equal to ms delta T. Whenever there is a phase change, you use Q is equal to ml. So here, this is ice, only temperature is changing. So Q is equal to ms delta T. M is 100 grams, S is half, and delta T is 50. This is 2,500 calories. So this is a phase change. Q is equal to mlf. That's 100 into 80. So this is 8,000 calories. This is again 100. S is 1 and temperature is 100. This is 10,000 calories. This is again phase change. Q is equal to mlv. This is 100 into 540. 54,000 there. Did you see how big that number is? And again, this is a temperature change. So 100 S is half for this and delta T is 100. This is 5,000 calories. Add them up, 64, 8, 72, 72, 5, 77, yet, yeah. So the total heat is 79,500 calories. Clear with this? Easy, just a formula substitution, nothing there. Next one. Be careful, last mate is not 200 degrees change, Abhinav, it's only 100 degrees ka change. You're going from 100 to 200. Principle of calorimetry. So it is another form of conservation of energy. So basically heat lost by the bodies must be equal to the heat gained by the remaining bodies. Yeah, kind of makes sense. So in an isolated system, the energy can't go anywhere. Now, there's another way of writing the same thing. In an isolated system, the net heat is zero. If you say isolated, meaning heat can't come in, heat can't go out. So the net heat gained or the net heat lost is zero. Clear with this? Let's see some questions on this. Get them. 17 and 17b. Thermal capacity means same as heat capacity. Mass of the block, you don't need it. Heat capacity, God. See, Q is equal to ms delta T. Question is not asking S, it is asking M into S. Specific heat capacity is different, heat capacity is different. Hope you remember. So basically heat capacity is directly Q by delta T, which is 4,500 by 50, which is 90 calorie per Celsius. That's it. I don't need the mass. So this body, if I give 90 calories, temperature will change by 1 degrees. What about B? Yeah. So in this, it is said both of them have same amount of heat. So Q is equal to MA, SA, TA is equal to MB, SP, TB. This is 300 into 0.8 TA is equal to 420 into 0.6 into TB. This guy is 240. This is 42 into 6. TB, 6 40. So you can clearly see TA by TB is 21 by 20. So TA is greater than TB. So heat flows from A to B. See, heat doesn't care where there is more heat. It is not like, heat flows from high heat to less heat. That's a wrong statement. So you mean to say water flows from more water to less water? So meaning if I take a big swimming pool, right, and water is like this, that's a lot of water there. If I take a small water tank here like this, right, and if I connect them with a pipe, there is more water here, less water here, so water should go here. No? Water doesn't care about that. Water flows from higher height to lower height. Temperature flows from higher temperature to lower temperature. So heat flows from A to B. B option. Clear with this? It has nothing to do with heat. So let's see one more. This is a good one, decent question. Let's get this. We have three liquids ABC, same mass, specific heats are not given, temperature 10, 25, 40. When A and B is mixed, temperature is 15, B and C is mixed, temperature is 30. If A and C are mixed, what is the temperature? Three. Yeah, it's not three, Abhinav. Sol and array, why do you guess? When did you become an astrologer? When I open astrology classes, I will let you know. For now, use science. Solve. Yeah, right, Ansh. Right, Niharika. Some of you are so strong in physics, you feel like there's no need to attend classes also nowadays. I hope that is true. Right, Daksha? Oh, just that is wrong. Let's see. Now when you take for A and B, now see here we can clearly see A ka temperature is less, so heat gained by A is heat lost by B. So mass is same, specific heat I don't know. Since you're gaining temperature, your final temperature is more than initial. You're losing, so your initial is more than final. I do know the temperature. How much is that? 15. This would be 40, sorry, 25. So we get SA is equal to 2 times SP. Similarly, when you do for B and C, M into SB, the final temperature is 30. M into SC, 40 minus 20, 30. The SB is also 2 times SC. Now when you do for A and C, M into SA, let the final temperature be T minus temperature of A is 10. C is definitely losing heat here because it has more temperature, 40 minus T. So take SA from here, substitute, take SB from here, SC from here and substitute. MM will cancel, SA will be 2SB. T minus 10, SC is SB by 2, 40 minus T. SB cancels out, you'll get 40 minus 40 is equal to 40 minus T. 16 degrees. You can do that, but they didn't ask you for specific heat. Clear, you know? So if you're mixing two liquids, it's fine. The problem comes, what if you're mixing like 10 liquids? Then how do I know who is gaining heat, who is losing heat? So let's see that one. This can be used as a general formula also. Let's say if n different liquids are mixed up, if n liquids of mass m1, m2, m3, so on till mn, specific heat capacity is S1, S2, S3, so on till Sn. Temperatures T1, T2, T3, so on till Tn. So masses are different, S is different, temperature is different, all are mixed. Find the final temperature. You can clearly see here, you can't tell who is gaining, who is losing heat. So how do we approach this? Think for a minute, then I'll show you. And what we get here will be a general solution. So tomorrow, if they give 7, 8 liquids to mix up, also you can use this formula. Sum of all masses, final heat, final mass, final gas. No, Ansh, you are right. You guys are not giving answers properly. Give me in terms of sigma, na? Summation. Ansh, you are right. See, the problem here is I don't know who is gaining heat and who is losing heat. So Now remember this thing, whenever we use this word, right, we don't know what is happening. Generally, think till not in all the problems so far, we always had this thing. Remember in two block problems also, when applied force, we don't know whether they're slipping or they're going together. Remember, anytime you had something like this and you didn't know, when a body is there and force F is there, we don't know whether the friction is front or back. So if you notice this theme, right, anytime we don't know what we do, we always start with an assumption. We said, okay, fine, since we don't know, let's assume all are gaining heat. So let the final temperature be T. I know all can't gain heat, but let max take care of that, which T, and let all gain heat. We did this thing in constraints also. We don't know how the blocks are going. We said let all the blocks go up. Then we wrote the constraints. The signs would take care of themselves. Let all gain heat. Then the first body will gain how much heat? M1, S1, T final minus T1. The second one will gain M2, S2, T final minus T2. So on, Mn, Sn, T final minus Tn. This is the net heat gain. But this should be zero because system is isolated. Agreed? All can't gain heat. So now if you expand this, you will end up with M1, S1 plus M2, S2, so on till Mn, Sn, T final minus M1, S1, T1, M2, S2, T2, so on till Mn, Sn, Tn 0. There. So we get T final will be sigma Mi Si Ti by sigma Mi Si. Good formula. Now here, for example, if T, what we got here, if T is less than T2, this term will become negative automatically. Isn't it? So the signs will take care of themselves. So you need not worry who is gaining heat and who is losing heat. Let the things take care of themselves. Have a look at this. So this is how you do if you have more than two liquids. Clear? Next one. The specific heat S is equal to 80 cube. Is some constant. T is temperature in Kelvin. M is the mass. Find the heat required. To change temperature from 10 degrees Celsius to 20 degrees Celsius. Easy one. Hmm. Roja got it and fell into the trap. He jumped into the trap. Who else? Anna also got saved. But you goofed up something else. You goofed up something else. So there's a road, there's a trap. You came like this, you saw the trap and said, yeah, and then you went and jumped here. Power 4 na, Hana? Easy one. So Q is equal to ms integral ms dt. M is m. S will be 80 cube dt. Limits temperature is in Kelvin. So this is 283 to 293. Be careful. Don't take temperature in Celsius. 10 and 20 look good, but T is in Kelvin. Generally, delta T doesn't have a problem, but when you have power fours and stuff, so you will have an issue there. So this guy will be MA by 4. That would be 293 to the power 4 minus 283 to the power 4. Numbers will be bad. But luckily in the exam, right, options will be in like this. Na? You'll see the options and you'll get a doubt. Ah, kuch to wrong hai. But be careful. This is given in Celsius. This is in Kelvin. Yeah. Clear with this? Easy one. There's nothing there. Next one. In calorimetry, now these questions are slightly different ones. Like if you ask me, these are the harder ones. Mixing of, ice and different substances. Let's say if you have 100 grams of ice at minus 20 degrees, is mixed with 100 grams of water at 70 degrees. Find the final temperature and the composition of the mixture. Composition meaning how much ice is there and how much water is there. Or everything became ice or everything became water. So same question. I will just change the number. What if this is 100-degree water? This is 70, this is 100. Everything else is same. Twenty grams of steam at 100 degrees is mixed with 80 grams of ice at minus 20 degrees. Find final temperature and composition. There, so you can keep on giving, but there I think this will give you the idea there. Let's do the first one. I'll give you a minute. Think about it. The problem here, now you can't use an ms delta t because there is a phase change, isn't it? There's m into l in the middle. So how do you approach this? Take a minute or two. Then I'll explain you the first one. Then I'll give you time for B and C again. Think how do you approach this? MSDT after 70 degree. See, you can use MSDT only when you're sure there is no phase change, but here ice is melting. Let's see the first one. Now listen, the problem here is since we don't know how much ice is melting, again, same thing, we don't know. That is the thing. Did you see the word? So when you don't know what to do, we assume. So let's assume everything has become 0 degree water. We will assume a common state. So we have 100 grams of ice. So listen carefully. One method. So you might have done in another way. I'm just showing in another way. And we have 100 grams of water at 70 degrees. So we'll assume 0 degree water is a common state. Why? I don't know. Since I don't know what is the final state, we'll assume this thing. Now, now to bring this ice to 0 degree water, you will not come directly. First, you will become 100 grams ice at 0 degrees, and then you'll become here. This guy will directly become this. So in this process, you are going to require how much heat? M into LF. No, temperature is changing, na? MS delta T. That's 100 into half. Temperature is 120. So you require 1000 calories to go from -20 to 0. Then Q is equal to MLF. That would be 100 into 80. That is 8000 calories. That means when this ice becomes water, you require 9000 calories of heat. Whereas this guy, Q, MS delta T, this is going to release the heat, which is 100, S is 1, and 70. This is giving 7000 calories of heat. This is released. Now, look at the final scenario. So, what do you have now? 100 grams. 100 grams became water. So, now the question becomes like this: I have 200 grams of water at 0 degrees. And how much heat do I have? The water released 7000 calories. And this guy absorbed 1000 calories to become 0 degree ice and 8000 to melt. I have a deficit of -2000 calories. Now, forget about all that water and everything. Now, this is a question. You have 200 grams of water at 0 degrees and someone removed 2000 calories of heat. What will happen to the water? It will freeze to ice, isn't it? From 0 degree water, if you remove heat, it will freeze to ice. Since heat is negative, water freezes to ice. So to compensate for 2000 calories, how much mass should form? Q is M into LF. So 2000 is equal to M into 80. That would be 25 grams. So therefore, your final answer, you have 175 grams of water, 25 grams of ice at 0 degrees. Temperature, it's a mixture. That will be your final answer. Is that making sense what we did? Suppose instead of -2000, if it is +2000, what will you do? You can ask yourself, I have 200 grams of water at 0 degrees and I'm giving you 2000 calories. Then what will happen? Temperature will rise. So we'll use Q is equal to MS delta T. Na? Is that making sense? See, you get only three options. Either you'll get negative, then what will happen? Water becomes ice. If you'll get positive, then water will boil. If you get zero, my assumption is right, isn't it? Answer question got over. Is that making sense? When you use this logic here, you get only three options. Either you'll get positive, you'll get negative, or zero. If you got zero, means your assumption is right. Everything has become 0 degree water. If you got negative, means the water will freeze to ice. If you got positive, water will boil to a higher temperature. Is this making sense, everyone? Anyone confused like, what did I do? Sure. Like using this logic, can you do BNC now? No, see, Puruja, to go to a lower temperature, what should happen? All the water must become ice. Then it will go down, isn't it? Phase change complete nahi hua. You're getting it? Until and unless all the water becomes ice, temperature won't change.
But sir, it's not always necessary that our assumption कि वो 0 degree पे है, that may not be right, right?
That is the reason we got a negative heat. If my assumption was right, I would have got zero here.
So sir, but how can you say that it is at 0 degrees then?
I don't know, na. See, that's what I'm saying. I'll start with zero. See, if this exactly became zero, that means what happened? All the heat absorbed must be equal to all the heat released. Then I would get zero. But I got minus 2000 deficient means what? I absorbed more, I released less. That means this state is not completed, na? You got stuck somewhere here only. You didn't even reach 0 degree water. Some part is still left in the form of ice.
But the final temperature will be 0 degrees.
Yeah, because you have 0 degree water and 0 degree ice ka mixture, na? Arey, when
Yes.
water is becoming ice, temperature won't change, but heat is absorbed or heat is released.
So, sir, is it possible that the final temperature, when we do such experiments, the final temperature will not be 0 degrees and it will be something else?
हाँ, it is possible.
तो
So
sir
वही बोल रहा
then
हूँ ना.
why
Suppose if this
would
is plus 2000, then what does it mean? You had excess heat, right? So the water won't be at 0 degrees, na? Then what will you get? 200 is equal to ms delta T. This would be 200, S is 1. So final temperature is 10 degrees.
oh yes sir, yes
समझ में आ रहा है? See, forget
yes
about the question. I'll tell you, see what happened here. Once I got till this part, forget about all this thing. Forget about all this thing. Now, this is a new question. You have 200 grams of water at 0 degrees, and I removed 2000 calories of heat. What will happen? Are you getting it? Try
yes
to
sir,
think
yes
that
sir,
way.
yes sir,
Now,
yes
forget
sir.
about the question, mixing and all, forget about it. So, this is what I created. Suppose if this plus 2000 means 200 grams of water at zero, I added 2000 calorie. What will happen?
Yes sir, I got it.
You're getting it. So, our assumption, right, won't give you the answer, but at least you'll get stuck somewhere. Na? Then you know what to do from there.
Yes
Try
sir.
for BNC. Yeah. Hmm, नहीं यार 10 नहीं है. Everything is water but not 10. Now I just changed the question. 70 degree water became 100 degree water. Now you'll get actually positive heat. Right, Vojus. Right, Ahana. Right, Ishana. Got it. Get the third one also. Ice and steam. Yeah, let's see. It will be the same solution. Everything will be same. This will change here. This guy would be 100. This would be 100. So this will be 10,000 calories. Now see, what I got now is 200 grams of water. Now forget about mixing and all that stuff. And how much heat you have? That guy released 10,000 and these people absorbed 9,000. So we have 1,000 calories of excess heat. Now this is the question. I have 200 grams of water at 0 degrees. You give 1,000 calories of heat. What will happen? Q is positive. Means you're boiling the water. Temperature rises. We'll use Q is equal to ms delta T. Now don't forget, how much water is that? 200 grams. It is not 100. 1,000 is equal to 200, 1 into delta T. There, T is 5 degrees Celsius. Making sense, everyone? Because when you melted 100 grams ice and 100 grams of water, you got 200 grams of water. Whatever you are giving is for 200. Right, Arush? Yeah. What about the third one? 20 grams of steam and this thing. No, that is wrong. And that is also wrong. Latent heat of vaporization is 540, huh? Why are you guys getting 38? Two people got 38. What mistake are you doing like to get 38? That's a pretty weird number. "20 grams of steam at 100 is mixed with 80 grams of ice at minus 20. Find the final temperature and the composition." Try. I'll give you 2 minutes. In calorimetry, one thing I noticed, these are the mixing of things. These are slightly tough questions. So the overall chapter is not really that tough. Right, Adi. It's not 44. Mm-hmm. 30 seconds more than I'll show you. It's not 44. 56 aayega, everyone. See why you're not getting 56. Right, Ishana, you got it. Taksha got it. I'm more interested, how did you get 38 actually? I guess forgot something. Let's see. So we have 20 grams of steam. 100 degrees. 80 grams of ice. At minus 20 degrees. I will take again 0 degree water as common state. You can actually take anything. I'm just taking 0 degree water as common state. Now this guy will become 20 grams of water at 100 degrees. Remember, before the temperature drops, you need to change your state. You have to become water. Then you'll become 0 degree water. This guy will become 80 grams of ice. Maybe you forgot this part. At 0 degrees. Then you melt into water, isn't it? Minus 20 degrees can't become suddenly 0 degree water. Minus 20 grams ice must become 0 degree ice, and then 0 degree ice will melt to 0 degree water. So see, where did you guys? You must have forgotten some term. That's why you're getting 38. So this guy will release a heat M into LV, which is 20 into 540. That's 10,800 calories. This guy will be ms delta T, which is 20 into 1 into 100. That's 2,000 calories. So this much heat is released by steam. This guy is 80, S is half, delta T is 20. So this is 800 calories. This guy is M into LF, which is 80 into 80, which is 6,400 calories. There. So finally, how much do I have? 20 plus 80. I have 100 grams of water. Again, see, that is a whole assumption. I'm assuming everything became water. I have 100 grams of water. And how much heat did this both give? This guy gave 12,800 calories of heat. And this guy absorbed only 7,200 calories. This is 3,600, 5,000, 3,000, no, that 2.8, 2.8, 5,600 calories. This much excess heat I have. Now you're getting the question? The question has become like, I got 100 grams of water and you're boiling with 5,600 calories. Q is equal to ms delta T. This guy is 5,600, m is 100, s is 1 and delta T. There. So temperature is 56 degrees, 56 degrees, everything is water. So to get 38, what did you guys forget?
10,800 plus 2,000 को 12,800 800 के बजाय 11,000 लिख दिया.
And two people did the same mistake.
10 का factor.
Clear with this? Yeah, so this is one type of questions, where mixing with water and all that stuff. Take a break. Come back by 7 2. We'll continue from here. Chalo, come back in 10 minutes then. Yeah, comes on your own. So there, that is about calorimetry. Next thing is KTG, kinetic theory of gases. Now, we'll not get into the proof of all that thing. That derivation is there, but it's not that important. We'll see that later on. But I hope everyone studied in chemistry. PV is equal to nRT. We'll play around with that part for today. We will see that assumptions and stuff maybe next time. So ideal gas equation. PV is equal to nRT. P is pressure. What is V? What is V? V is the volume in which molecules can freely move. V is not the volume of the container technically. Do you guys remember that real gas equation? You get term, V minus NB करके एक term आएगा. If you have studied that NB represents the volume of the molecules. Freely move. But in an ideal gas equation, volume of the molecules is negligible. So therefore, we can say V is the volume of the container. So V is the volume of the container, but this is the thing. V is actually something else. N is number of moles. R is gas constant. T is temperature in Kelvin. Gas constant का value is 8.3 joule per mole Kelvin. So we use this thing. Don't use our chemistry का stuff. Clear with this? Then let's see some question on this. That's it. We're just going to play with that one equation. The important thing is the graphs. So if you have a PV graph, V naught to V naught, P naught to P naught. This point is A, B, C, and D. So it's like a kind of like a square. So using this graph, I want you to plot P T graph, V T graph. Did you guys do anything like this in chemistry? If one graph is given, draw the another graph. Try. I'll give you a minute or two. Try to draw PT graph. Then I'll tell you something. Then I'll give you more time. First, you think about it and give it a try for a minute. Let's start with the PT graph. It's an ideal gas equation. PV is equal to nRT. How do you think it looks? Think how to draw this, then I'll explain you a few things. Let me explain you something. See, now in the ideal gas equation, PV is equal to nRT. Now, I'm sure you studied in chem. We were going to do this anyway later on in thermodynamics. You know what is isochoric process? So isochoric process meaning constant volume. So meaning V is constant. So we'll get P is equal to nR by V. So if you look at this graph, the slope will be nR by V. Means in a PT graph, so if you're drawing pressure versus temperature, an isochoric process will pass through origin like this. You're getting it? So in a PT graph, an isochoric process will look like a line passing through the origin. Can you tell me which volume is bigger, V1 or V2? Look at this thing, slope. Slope is proportional to 1 by V. More volume, lesser the slope, isn't it? So here V2 is greater than V1. Are you getting this? So if someone asks you to draw an isochoric process in a PT graph, it looks like this. How does an isobaric process look like? What is an isobaric process? Pressure is constant. Meaning, if I have to show you a little more, see, for example, how does it look in PV graph? How does it look in VT graph? In PV graph, it will look like this. V1, V2, V2 is greater than V1. In VT graph, it looks like this. V2, V1. Are you getting it? An isochoric process will look like this in PT graph, like this in PV graph, like this in VT graph. Is this making sense, everyone? So you should know how each process will look in different graphs. The same thing if you do for isobaric process. So we get V is equal to nR by P into T. The slope is proportional to 1 by P. Same story. If you draw a VT graph, if you draw a PT graph, or if you draw a PV graph, this would be a line passing through the origin. This is P1, this is P2. P2 is greater than P1. They will look like this only here. So that is kind of actually useless. So we'll not draw that. I hope that is making sense. How does isothermal process look like? Isothermal process, temperature is constant. So we get PB is equal to constant. This is a rectangular hyperbola. Look at this thing. PV constant. If V is 0, P is infinity. If P is 0, V is infinity. So we get graphs like this. This is T1, this is T2. These are called isotherms. So any point on that curve will have same temperature. Who has more temperature? Think about it. If the temperature is more, means constant is more. If constant is more, meaning the graph will be far from origin, right? So the farther the curve from the origin, the more the temperature. So the isotherms which are far will have more temperature. And that's how you see. So check out these graphs. You should have an idea about these things. They do ask a lot of questions on this. So this is how the curves will look like. Any doubts on this page? Clear? You should know how a constant volume will look like, how a constant pressure will look like, how will a constant temperature look like. All clear? Now can you try PT graph? I'll give you a minute, then I'll show you. Now, just to give an idea here, look at this thing. So in a PT graph, look at this. What is this BC? Isobaric, na? BC and AD are isobaric. This AB and CD are isochoric. There, just now I showed you how to draw them in a PT graph. Now try. So this thing what I gave you has two isobaric and two isochoric processes. Should I help you with one? See, this is how I draw. We want to draw PT graph, no? First thing, the isobaric process. How will they look? They will look like this only, horizontal lines. So who has more pressure? BC, so that is above, and this guy is AD. Great. The other two lines are isochoric, so they should pass through origin. They will go like this, and they will go like this. Now, which line is which one? Who has more volume? CD has more volume than AB, right? Higher the volume, lesser the slope. So this guy is CD and this guy is AB. Is that making sense, everyone? Now look at the point of intersection. So this is interaction between AD and CD. So this must be D, this must be A, this must be B, and this must be C. Now I'll just redraw it again. There. This is A, this is B, this is C, this is D. It is important. The arrows are important. This is not a parallelogram. A, B, and CD are not parallel. They're lines passing through the origin. This is your final answer. This is how the graph would look. Is this making sense, everyone? Now, can you draw VT graph? This is PT. This is how it looks. Now you try for VT. Anyone confused with this, please ask me. So here you can clearly see CD ka volume is this volume is V naught and this volume will be 2V naught. So this will have less slope in PT graph. So that is how you decide. I know they'll pass through origin, but I don't know which line is what. And that numbering is important because in the option there'll be two graphs where ABCD will be like this and ABCD will be like this. So you should know whether it's a clockwise or anti-clockwise arrows. Draw VT graph. I'll give you a minute. But anyone confused with this thing, ask me. We are just playing with the PV is gold NRT. It will be reversed, right? Yeah. Let's see. We are drawing VT graph. So isochoric, the red lines will look like this. Isochoric. Who has more volume? CD. So this upper line is CD. This line is AB. This is 2V0 and this is V0. We know isobaric will pass through origin. Actually, the graph kind of looks the same. Whoever has more pressure will have less slope. So who has more pressure? BC. So this guy is BC and this guy is AD. Look at the intersection. This point is A, this point is B, this point is C, this point. Arrows have changed. That's why I said the arrows are important. That itself will be an option. So if you look at the graph, this is a green one. This is a green one. This is A, B, C, D, and back. Check. Clear, everyone? Isobaric will pass through the origin. Like it's a VT graph. Clear, na, Nikhil? Sharman? Got this? Soham? Surya? Vignajit? Ojas? Arnav? Ishana? Ahana? Adi? Clear? Abhinav? Arya? All got this? Arnav, clear, na? Let me give you one more like this. Suppose this is a VT graph. This is A, B, C, D. Can you plot PV graph? I gave you VT, I'm asking for PV. Mm, just solve now, Abhinav. Why do you want to find coincidences? Instead of VT graph, what if I ask you TV graph? Then what will you say? Finish all this question, then we can see. Show you. So PV graph. Now look at here. So I'll just mark them with red. These are isochoric. So they will just look like two lines. Whoever has more volume, BC will be here and AD will be here. These are isothermal. So in isothermal here will be like this. They'll be hyperbolas, no? They look like this. So whoever has more temperature will be the farthest. So this guy is CD and this guy is AB. This intersection is A, this is D, this is B, and this is C. This is normally how I draw. I just draw all the four curves and then I take the intersections. This way there's no confusion who is what. So these are again going anti-clockwise. So why are the arrows this way? Maybe there is a sequence, there is a pattern, but okay, that's really not that important. Clear with this, everyone? They can keep playing like this, they can keep asking all weird graphs also. Something like this. Later on, we will see, we'll have curves like this also, hyperbolas and all that stuff. But this is important. You can convert one graph to another. Next one. We have a PV graph. This is A, B, C. The question is, how does temperature vary on AB? So when you go from A to B, how does the temperature vary? Options, it'll increase, it'll decrease, it'll increase and decrease, it'll decrease and increase, it'll remain constant. Is our options. BC and CA, and at which point the temperature is maximum. So in this process ABCA, at some point temperature will go to maximum. Which point is that? That's it. There are no numbers, nothing. It's a theoretical one. So they will give you a graph like this and they'll expect you. That is right, Purvaja. Get the first part also. So how does the temperature vary when you go from A to B, when you go from B to C, when you go from C to A? So those are three questions. That is right, Vehan. नहीं विहान, AC is wrong. इसमें सबसे AC is the good one. I think I'll give another minute and then I'll show you. In a PV graph, you're asking about temperature. So how do we even proceed? Let's see. All right, Ishana. C2A temperature. Right, Puraja. Now see, these kind of questions, right? First need to ask yourself, in a PV graph, how do you get temperatures? Isotherms, isn't it? So that's what you're going to do. Let's say let's draw some hyperbolas, basically isotherms. Like this. So let's say if this is T1, I didn't draw properly, but T2, T3, T4, T5, and T6. Can you see? The farther the isotherm, higher the temperature. So from here, I can say T6 greater than, T5 greater than, T4, T3, T2, and T1. This everyone agrees? So now when you're going from A to B, see what is happening. This point A is on isotherm 2, then you're going to isotherm 3, then you're going to isotherm 4, 5, and 6. So when you go from A to B, you are continuously going to higher and higher isotherms. So on AB, temperature continuously increases. And you can clearly see B is the highest temperature, isn't it? The point on the farthest isotherm is B. And when you're coming from B to C, you're from 6, you're coming back to 5, 4, 3, and 2. So on B to C, temperature continuously decreases. Now when you go from C to A, look at this. You're at 2, you're going to 3, this is 4, then you again come back to 3 and 2. So you go to higher isotherms and then you come back to lower isotherms. Temperature increases and decreases. And temperature at B is maximum. That is at the farthest isotherm. There. This is how you solve these kind of questions. Anytime you give me a PV graph and you talk about temperature, draw hyperbolas. The farther the hyperbola, the higher the temperature. Is this clear, everyone? How do you know there is nothing? I just drawed one. I just want to know whether it's increasing or decreasing, right? So I just drew a thing. I know that 2, there's no guarantee that is an isothermal 2 and 2. You're saying about AC, na? That I took randomly, Rehan.
So
It won't matter, na? Why will that answer change because of that?
So if it didn't end up on the isotherm it started on,
then try and tell me what will be the answer then.
Okay, so we can say increase, decrease.
इतना तो बोल सकते हो ना? Why do I care whether it is starting or not? This line will definitely go to higher isotherm, then come back to lower isotherm. That much I know. I took 2 and 2 so that for you guys it will be easy to understand. But what you're saying is true. There's no guarantee ends here on isotherm. All clear with this? Let's see something better than this. So it's the same question, but we have a better variation. This could be advanced ka more than one choice question. So we have a PV graph. This is V naught. This is 3V naught. This is P naught and this is 2P naught. This is A, B, and C. Same question. How does temperature vary on BC? Find the maximum temperature in this whole process. I wanted to find the maximum temperature. I don't want to where. I want the maximum temperature. So when this gas goes from ABCA, At what point you get the maximum temperature? N moles of gas? It's an ideal gas. That is right. Let's find the maximum temperature. Yeah, it would increase and then decrease. The isotherms will be there. Now, how do you find the maximum temperature? Be careful, there is no symmetry. I messed up the numbers. You know how to make this an easy question? If it was a mains question, you did that. If this was 2V naught, if that was 2V naught, then I can say by symmetry it will be the exactly midpoint, isn't it? If that was 2V naught, your life would have been easy. You could say it's a midpoint and finish off. So this will be 3V naught by 2 volume and 3P naught by 2. And then you can use PV is equal to nRT. 3P naught by 2, 3V naught by 2 is equal to nRT. So that will be the maximum temperature. If that was 2V naught. Making sense? But that is not 2V naught, that is 3V naught. Now what to do? This is what makes this question an advanced more than one choice. The first part was easy. You can draw an isotherms. So mathematically, if you ask me, right? So there is one particular hyperbola for which this BC becomes a tangent, isn't it? So it touches only at one single point. That would be the maximum temperature, but I can't use that to solve. You can clearly see here, you're going from lower to higher isotherm and higher to lower isotherm. So this thing you can see. So on BC, temperature would increase and then decrease. So when the line BC becomes a tangent to a particular isotherm, that is the maximum temperature. Now what? How will you proceed? Think I'll give you a minute or two. It becomes a mathematical problem. 25. Right, Ishana, you got it. We have one answer, everyone. Did you do maximum minima? Did you do? Maximum minima करना पड़ेगा. I'll give you a hint. See, can you find the equation of the line BC? That will give you the relation between pressure and volume. Then I know PV is equal to nRT. Right, Vihan, we got it. So Look at this thing. If I take the coordinates of C, this guy is 3v naught comma p naught. This guy ka coordinates are v naught comma 2p naught. This kind of looks like x1 y1. This kind of looks like x2 y2. So x ka place mein we have volume and y ka place mein we have pressure. So we can find the equation of a line y2 minus y1 will be y minus y1 will be y2 minus y1 by x2 minus x1. That is the slope into x minus x1. So here y ka place mein we have pressure. Y1 is 2p naught. Y2 minus y1 is p naught minus 2p naught by x2 minus x1 is 3v naught minus v naught. X ka place mein volume v minus v naught. So this gives you pressure is 2p naught minus p naught by 2v naught into v minus v naught. So there, this is the relation between pressure and volume on that straight line. And I also know ideal gas equation PV is equal to nRT. The problem here is the temperature is depending on both pressure and volume. So I don't know what to do, but I can eliminate pressure now. This is 2p naught minus p naught by 2v naught. V minus v naught into v by nr is equal to temperature. So there I got temperature in terms of a single variable volume. For maximum minima, we have to differentiate. It becomes more of a max question. So dt by dv must be 0. So just send it inside. You'll get 2p naught v naught 1 by nr 2p naught v naught minus p naught by 2v naught v square minus v naught v. If you differentiate this 1 by nr, this will become 2p naught minus p naught by 2v naught 2v minus v naught. This is equal to 0. This will be there v naught will be 5 by 2 v, meaning at this volume you're going to get maximum pressure. Which is 2.5 v naught. That means if you look at this point here now, it is not in the center, it is somewhere here. This point you're getting maximum temperature. It's more closer to that 3. I think once you got this, it is just a matter of take this guy and dump it in this. From here you will get T max is equal to, if you substitute there, how much will I get? 5 by 2 v naught. So that will be 3 v naught by 2. V naught, v naught will cancel. 3 by 2. 2 minus एक बाहर भी एक v naught है. That would be 3v naught by 2, 5 by 2, so 3 by 2, 3 by 4, 2 minus 3 by 4, 4, 2, 8 minus 3, 5, v naught by 4, 5 and 5 is there, 25, p naught, v naught by 8 nr. That's your maximum temperature. Clear with this? Clear, everyone? There, this is how they can play with graphs. Next one. It's more of a max. The main thing you need to figure out, because it's a straight line, find the equation. I know ideal gas equation there. I know 2 equations. Eliminate pressure, I get T in terms of V, then it becomes maximum minimum. It's a lengthy equation. Clear? So there's no symmetry. This is how you do. If it had been 2V naught, your life would have been easy. Any doubts on this? Clear, na, Ansh? Got this? Next one. So this is one type of questions based on graphs. Now they can also ask you physical systems. So let's say we have a piston here, piston here. The whole thing is insulated. Between them, we got a spring here. It's a vacuum. So here there is some gas, here there is some gas. 1 mole and the temperature is 300 Kelvin. This is also 1 mole and temperature is 300 Kelvin. This distance is 1 meter. This distance is 1 meter. The middle ka distance I don't know. Initially spring is compressed by 1 meter. Because the gases will push the spring, na? So they will push the spring. These pistons are massless and smooth. Now what you did, you change the temperature on both the sides. So on the left-hand side, temperature became T1, which is 400 Kelvin. On the right-hand side, you made the temperature T2, 500 Kelvin. So you did something and the temperature is changed on both the sides. So temperature on the left container become increased to 400 Kelvin and 500 Kelvin. Now, when you increase the temperature, pressure increases. So they will start pushing the spring more. So find the final compression in the spring. So initially spring is compressed by 1 meter. Now, because you increase the temperature, pressure will increase, they'll compress the spring more. What is the final compression? The gases are ideal. This is how they'll frame question. This is the difference between physics and chemistry. The ideal gas equation. PV is equal to NRT we use, but in physics we bring mechanics. I know you guys have been missing the spring from long time. So the moment you saw the spring, somewhere you had a happy feeling like, oh, spring, you're back. Let's get this. This would be an advanced question. Think how will you solve it? I'll give you 3-4 minutes. It's a worthy question. Like I keep saying, always draw the final diagram. That will give you the clarity. And start from there. Think. Give it a try. Just give it a try. I'll get some water and come. Don't worry about the question. Focus on getting the final diagram. So you have to ask yourself few questions. Will both the pistons move same distance? Right? After this situation, will the pressures be, what will be the pressures? What will be the volume? Number of moles will they change? So that's the thing. It's not about solving. You need to keep asking questions. Okay, what is this? What is that? Which equation is valid? So focus on that. Don't worry about getting the answer. Answer is a consequence. When you ask the right questions, you'll get the right answers. Try. I'll give another 2-3 minutes. Draw the diagram. Try to figure out as much as you can. Let's see the final diagram. See whether you figured out the diagram though. Answer is not a good number. So let's see. Final temperature is T1, T2. Final pressure is P dash and P dash. Do you agree both will have same pressure? If they don't have same pressure, this piston will keep moving, right? System is in equilibrium. So both दोनों gases में pressure must be same. And let this thing expand by 1 plus x1. Let this expand by 1 plus x2. So there. So let gases expand by x1 and x2. Now we don't know x1, we don't know x2. So if I can find x1, x2, my job is done actually. So the new compression will be initially already it is 1 meter compressed. So 1 plus x1 plus x2. There. So this is how to find. So if I can somehow find x1 plus x2, my job's done. And for convenience, let's call x is x1 plus x2. So if I can find x, my job's done. Got till here? Did you guys figure out the pressure is same? Final pressures must be same since the pistons are at rest. And they're smooth and massless, or else they would have moved. So totally how many variables are there? P dash, x, what else? Volume also we don't know. So yeah. Now what? Spring constant also we don't know. Root 4 plus root 5 by root 3. That's not the answer. Sequence is good though. If you try to draw the FBDs for the initial piston, what is the FBD? Now I don't know the initial pressure also. So let the initial pressure be P. This is also P. So this guy would be P into area. Area I don't know. The spring force will be K into 1. So we get P into A is equal to K. This is equation 1. Second thing, I'll apply ideal gas equation. PV is equal to nRT for any one compartment. So pressure is P, area volume is A into 1, N is also 1, R, temperature is 300. So I have P into A is 300 R. This is equation 2. So this is initial state. Now I can do the same thing for final also. Final equation, when you draw the FBT, this guy will be P dash into A, and this guy will be K into 1 plus X. So P dash into A is K into 1 plus X. This is equation 3, because the thing is in equilibrium. And what about the ideal gas equation for the left compartment? More space. For the left compartment, the ideal gas equation will be P dash, volume will be A into 1 plus X1 is equal to number of moles 1, R, temperature is 400. That's your equation 4. For the right compartment, so you can actually use the ideal gas equation initially and finally for the two compartment. That will give you 3 equations, and you'll get 2 equations from the FBD of the piston. Pressure is same P, area, the volume is 1 plus X2, area into this, 1, R, and 500. This is equation 5. There, I got 5 equations. Now in this, I want to eliminate x1 and x1 plus x2 is x I know. So if you add equation 4 and 5, you will get x1 plus x2. Have a look at the equations first of all. You got the equations, question is over. It's a matter of solving now. Now from all these things, I want to find x. So I don't want p, I don't want p dash. That looks possible because 1 and 2 may p is gone. I can add these two and divide this, so p dash will also be gone. Have a look at the equations. So initially both the gases are identical, so you'll get only one ideal gas equation. Finally, you'll get 2 different ideal gas equations because temperature is different. Initial piston ka 1 equation, final piston ka 1 equation. Total 5 equations you'll get. So 2 force equations and 3 gas equations. Then from here, add equation 3 plus equation 4. This will be P dash A into 1 plus x1 plus 1 plus x2 is equal to 400 R, 500 R, 900 R. This guy will be P dash A into 2 plus X is equal to 900 R. So divide this by equation 3. What is equation? Equation 4 by 5. This is 4 plus 5. If you look at equation 3, that was P dash A is equal to K into 1 plus X. So if I divide these two, I'll get 2 plus X is equal to 900 R by 1 plus X. And take equation 1 and 2. Equation 1 PA is equal to K. Equation 2 PA is 300 R. There is a K here actually. From here, K will be 300 R. Substitute there. 2 plus X into 1 plus X is 900 R by K is 300 R. That would be 2 plus X square plus 3X is equal to 3. X square plus 3X minus 1 is equal to 0. x is equal to -3 plus or minus root over 9 plus 4 by 2. -3 plus or minus, take the +1, root 13 by 2. So the final compression is 1 plus x. That would be -1 plus root 13 by 2. Yeah. Making sense, everyone? Look at the equations. The main thing is the equations. If I add these two, x1 plus x2 will become x. Then I divide with this thing, so p dash will go off. Divide these two, p will go off. I'll get k ka value from equation 1 and 2. Take that and substitute in equation 3, 4, 5 ka thing, and you're done. This is what makes this question an advance. It's lengthy. It is a little tough also. You need to figure out the equations and stuff. There, that's how you can mix up ideal gas equations with mechanics. This is more of an equilibrium problem. Clear with this thing? Okay, so that is there. So with that is the last one for the day. So on Thursday when we catch up, we'll continue from here. So on Thursday mostly we will wrap up the KTG. We will do a few more problems like this, and then we will see ideal gas ka assumptions and all. There is a proof on PV is called NRT for boards, but we don't need it because that is only in 11th, 12th maybe nahi hai. So we will ignore that part. Okay, so that will wrap up for the day. So any doubts, anything you can stay back and ask, also free to leave. I will see you on Thursday at 5:30 as usual. So take care, stay safe, and make sure to give the exam. The deadline is Friday night. So